Hello everyone. Welcome back to Buttery Game Theory. Mastering Advanced Game Theory Episode 4, Perfect Bayesian Equilibrium. Today, we'll learn how to navigate extensive form games with incomplete and imperfect information using the Perfect Bayesian Equilibrium. Let's revisit our startup founder scenario from last time, where Alice decides whether to invest in a new technology, and Bob decides whether to fund it based on Alice's actions. Now, let's add a twist of uncertainty. Before Alice even makes her investment decision, let's imagine that nature steps in and determines Alice's type. The high-risk type means she's more optimistic about the potential returns of the technology and might invest even if the initial signals aren't great. Meanwhile, the low-risk type Alice is more cautious and will only invest if she sees strong positive signals. Bob, the investor, doesn't know Alice's type. He only observes whether or not Alice actually invests. This is where the incomplete information comes in. Bob doesn't have full knowledge of the game's initial conditions, or Alice's type. Furthermore, if Alice does invest, Bob still doesn't know why she invested. Was it because she's a high-risk type who would invest anyway, or a low-risk type who saw something promising? This creates an imperfect information scenario for Bob. He doesn't know the exact history of the game when he makes his funding decision. Now, to calculate the perfect Bayesian equilibrium, we need to understand these concepts. 1. Information set. An information set is a collection of decision nodes that a player cannot distinguish between at the time of making a decision. In our example, if Bob observes that Alice has invested, his information set contains the node where a high-risk Alice invested and the node where a low-risk Alice invested. It can be represented by a circle or a dotted line like this. 2. Beliefs. In games with incomplete information, a belief is what a player thinks is true about something they don't know for sure. Since Bob doesn't know Alice's type, he forms beliefs about the probability of being at different nodes within his information set. Bob will have a belief, let's say beta, that he is at the high-risk Alice invested node, and consequently a belief of 1 minus beta that he is at the low-risk Alice invested node. These beliefs are crucial because they drive Bob's expected payoffs. 3. Types. A type refers to a specific characteristic or piece of private information that a player possesses and that is relevant to the game. Here, Alice has two possible types, high risk and low risk. Nature determines her type before the game begins. 4. Strategy profile. Just like in Nash equilibrium, a strategy profile specifies the strategy for every player. However, now we need to consider that Alice's strategy might depend on her type. So, a strategy profile will include a strategy for the high-risk Alice, a strategy for the low-risk Alice, and for Bob there will be two strategies. One is for when Alice invested, the second is when Alice did not invest. Also Bob's beliefs about the probability whether Alice of high risk or low risk type. Perfect Bayesian equilibrium. Now, what exactly constitutes a perfect Bayesian equilibrium? A strategy profile and a system of beliefs form a perfect Bayesian equilibrium if they satisfy the following conditions. Sequential rationality. At each information set, the player whose turn it is must choose an action that maximizes their expected payoff, given their beliefs at that information set and the subsequent strategies of the other players. Belief consistency. Where possible, beliefs at each information set must be consistent with the player's strategies and the rules of the game. Specifically, at information sets reached on the equilibrium path of play, beliefs are determined by Bayes' rule and the player's prior beliefs and their chosen strategies. At information sets that are not reached on the equilibrium path, or off the equilibrium path, beliefs can be arbitrary, but they should still be reasonable. Alright, let's now focus on our example. First, nature determines Alice's type, either high risk with the probability of p, or low risk with the probability of 1 minus p. Alice observes her type, and then chooses one of two actions of either to invest or not. Bob observes Alice's action, but not her type. He then chooses between funding or not. So, Bob has two information sets, one for when he sees action invest, and another for when he sees not invest, but in both cases, he does not know whether Alice is high risk or low risk. To find the perfect Bayesian equilibrium, we need to figure out the strategies for each player and their beliefs. In our example, both high and low risk Alice can choose to invest or not, while our second player, Bob, can choose to fund or not depending on his observation on the first player's action. While after observing that Alice invested, Bob forms a belief that Alice is high risk with probability mu and low risk with probability 1 minus mu. After observing that Alice did not invest, Bob forms a belief that Alice is high risk with probability beta and low risk with probability 1 minus beta. We now calculate the best responses for all player, bottom up. Starting with Bob's expected utilities, seeing Alice choose to invest. Given Bob's belief mu, where mu is between 0 and 1. Here funding is strictly dominating, not funding, so Bob will choose to fund after seeing Alice invested. We also calculate the expected utility when Bob observes Alice did not invest. Given belief beta, his best response is not to fund. Now using the sequential rationality, we look at Alice's best response. Knowing Bob's strategies. High-risk Alice can either choose to invest and get 4, or not and get 1. Her best response is to invest. Meanwhile, the low-risk Alice can invest and get 2 or not invest and get 3. She will choose not to invest. Belief consistency. With the assumption that P is more than 0 and less than 1. And since high-risk Alice plays invest, and low-risk Alice plays not invest, both Bob's information sets are on the equilibrium path. Now let's determine Bob's beliefs mu and beta. Let the probability that Alice is high-risk be P is between 0 and 1. Since mu is the probability of Alice invests if she is of type high-risk, therefore we can calculate mu and get mu is equal to 1. Similarly, beta is the probability of Alice invests if she is of type low-risk, therefore we can calculate beta and get beta is equal to 0. Now we have the complete version of the strategy profile, and the perfect Bayesian equilibrium that satisfy this strategy profile is 4 and 3, for when Alice is of high-risk type, and 3 and 1, if Alice is of low type. So that's it for today. Thank you for watching and see you in the next episode.